Okay, so let's discuss the edit distance algorithm. So, given what we have been discussing, maybe it would be nice to think that how do we transform this problem into a recursive algorithm, right? How do we use a recursive algorithm to solve this problem? So, we have two strings. We have strings alpha and beta, and we have characters. Let's define them as x and y. Okay? So let's say that our strings, our string x is equal to alpha x, i.e., the alpha here is the prefix of x, and the beta here is the prefix of y. All we need to do right now is formulate some logic so that the problem, when the function takes in these two strings x and y, we could transform the problem into a smaller instance of itself. Okay, that's what we do in recursion. Okay, so what we're trying to do here is something that we tried to do in the longest increasing subsequence problem. We look at the last character, we determine if this last character is parts, we do some processing on this last character, and then we pass the prefixes onto another call to itself. Okay, so let's take x and y, and let's think about the optimal edit distance between x and y. Okay, what would the optimal edit distance be between x and y? Well, there's a couple options, right? Let's look at just the last characters. If we look at just the last characters, the optimal edit distance, if both the characters are matched to each other, right? If they're both matched to each other in the optimal alignment, then assuming alpha and beta also are matched together in optimal alignment, if they're matched together in optimal alignment, this is one possibility for the optimal alignment of the strings x and y. It's also possible in the optimal alignment of x and y that the last character of x is not matched to y. In that case, we have this possibility where we have a deletion here, where we have a space here. Make sense? Or it's also possible that the last character of y is not matched to x. In that case, we have a insertion. Okay? So we have three different possibilities. We have either an insertion, a deletion, or a transformation. Okay? So this seems like we could use this knowledge to set up a recursive call, right? Because we have one of three options. Plus we have a smaller set of inputs that we could send to another instance of ourselves. Okay? So, three cases, xm and yn are matched. Again, remember the strings are not necessarily the same size. So we have the case where xm and yn are matched. We have the case where xm is unmatched. So this is the deletion instance. And we have the case where yn is unmatched. So we have a gap penalty, or a mismatch cost. Okay, so we write this in terms of a recurrence. Same thing as we did in the longest increasing subsequence, right? We write a function, and let's write a function opt that takes in two strings, or more correctly, it takes in two string prefixes, and it says the optimal alignment of these two string prefixes of x1 to xi and xy1 to j is equal to either the case where they're both matched, i.e. you pay some transformation cost and nothing else, or the case where you have a deletion, or the case where you have a insertion. Okay? And this is, of course, assuming one major thing. This is assuming, oh, never mind. Well, this is assuming if x and y, if the last characters xi and yj are if they're the same character, let's say if xi is equal to yj, then this alpha is equal to 0. Else, the alpha is equal to some cost. Okay, so the major thing remember here is that this alpha isn't a cost, like isn't a number like 1. It's not delta. Okay, this delta is actually equal to a integer, to a particular cost. But this alpha, it could be 0, or could be something, an integer. Make sense? So, of course, with this recurrence, we need some base cases. And the base cases here are again obvious. Again, similar to how we were doing the longest increasing subsequence. If one of the elements goes to 0, if one of the prefixes is empty, then what happens? Well, if y is empty, if there is no y, then the optimal cost, the optimal alignment cost is a bunch of deletions. Right? Similarly, if there is no x, then the optimal alignment cost is a bunch of letter insertions. But they both still have that same gap penalty. Make sense? So we have a particular algorithm. We have an algorithm. We have a particular algorithm. We have two inputs. X, we rewrite x as A and y as B. And thus, we compute the three different possibilities as recursive functions, as recursive calls, M1, M2, and M3. And we say, and remember, this cost here, this cost function is 0 or 1, or greater, I should say, or greater, depending on if characters match or not. And then we simply return the minimum of these three costs. And that's just how it works. Okay? So let's try to do that visually. Let's say we have two words, dread and deed. Okay? And the first thing we do is order the number of subproblems as a table. Okay? So what does the table here of edist look like? Well, it just looks like we have to have each of the inputs into here. Each of the second input is one of n prefixes of B, and we have one of n prefixes of A. So we just have one of n prefixes of B and one of n prefixes of A. And then we just fill out the base cases. We say, if the prefix B is equal to an empty string, then the cost of alignment is simply the number of letters in the prefix of A. Similarly, and this should be 4. Similarly, we have the same thing here. Okay, so we have the base case. We have the base cases all filled out, and the next thing we need to do is fill out these elements here, row by row. Okay, so row by row, if we go and let's make this row by row, we calculate each of these different values. Opt I minus 1, opt j, the mismatch cost, the gap cost, plus the optimal alignment. And we get the following. We fill out this row. So for instance, over here, we know that we have three options. We have either, and a good way to do this is ij. Okay, so 0, 1, 0, 1. So we either have the minimum in this particular case. We either have the minimum of alpha plus this value here, or it's delta plus this value here, or it's delta plus this value here. Okay, makes sense? So same thing with this value. We either have alpha or delta plus this, or delta plus this. Or, sorry, blanking on writing delta, man. Okay, so we have three potential costs. So in this case, alpha plus this would be 3, delta plus 1 would be 2, or delta plus 3 would be 4. So you take the minimum cost of these and you get 2. Okay? So does this make sense? Yeah. Let's look at this. Is the minimum alignment of D with DRE, is that 2? And yeah, so we have D and we have DRE. Yeah, that makes sense. It is indeed 2. Okay? So the important thing to note is that the alignment is dependent on the row to the northwest, is dependent on the element to the northwest, the element to the north, and the element to the west constantly. Okay, so as long as we have our base cases here, we just go down to the next row, and then we go from left to right and fill out the next couple columns. And we do that again and again and again until we reach this final point, where we find that where the table says that the optimal alignment between deed and dread has a cost of 2. And is this correct? I mean, I think it is. Let's do this out. Deed and dread. R-E. Oh, nope. Oh, yes, but R-E. Sorry. R-E-E-D. R-E-A-D. Okay, so this would be the optimal alignment. We have 3 matching characters here, and we have 1 insertion and 1 change. Okay, that does appear to be the optimal alignment, and that's actually what the algorithm gives us. Okay, simple as that. So as long as we have, and there it is. So as long as we have the actual, the major point here is as long as we have a recurrence that makes logical sense, and we know that we could order the subproblems so that we're always referring back to a subproblem that has already been calculated, then we should be able to get the correct result. Okay? So one thing before, I mean, one thing that was related when we discussed longest increasing subsequence, this tells us the cost of the optimal alignment. Do we know what the optimal alignment actually is? Yeah, we do. And we know what the optimal alignment is by the actual direction of the arrows we take. So for instance, over here, we know that we took these arrows when we took the matching penalty when we took these arrows. So we just determine, like we did with longest increasing subsequence, we just have a pre symbol. And a pre symbol tells us which one of these minimum cases we took. So depending on the minimum case we took here, this will tell us, depending on the minimum case we took, this will tell us, and I know I'm in the way, depending on the minimum case we took, this will tell us, did we match two characters together, as we did here? Did we match two characters together? Did we match two characters together? Or did we do a deletion? Or did we do an insertion? Or did we match two characters together? Right? So again, if we keep track of the actual elements in this case statement, if we keep track of the actual case that was the minimum cost, then we could recreate the actual alignment of the actual minimum alignment, okay, in the same amount of time, in the same running time. So there is no real search that we have to conduct. Okay, so hopefully that makes sense. Well, let's finish this out. Let's finish this up. So the dynamic programming algorithm for edit distance simply is that the cost of aligning another character against another. We have two costs. The cost of aligning being two characters that are mismatched, that is something, and the cost of aligning two characters that are matched. And then we have the price of deletion. So we have this following dynamic programming algorithm. Again, remember that we created a table for every possible prefix of A. We have a row for every possible prefix of A. We have a column for every possible prefix of B. And then we started off by filling in the base cases. And then all we do is simply loop through the table and calculate the recurrence that we came up with. Okay, so what is the running time of this? Well, we have two different for loops. So we have O of n squared. And this right here, how long does this take? I mean, this is just constant, right? O of 1, right? It's just a constant calculation. So the running time is O of n squared. And the space used is O of n squared because of this right here. Make sense? Sorry, let me just make sure. Yeah. Okay. So let's put a pause here, and then when we come back, let's see if there's something we could do about this space used. Thanks.